main theorem, and we'll talk about ideas for how to prove it. Just to review, the slide was on the last talk, so I won't really read it again. But here's the Boltzmann equation again, and here's the collision operator again, and here's the collision kernel again. And our main focus is again this angular singularity, so this behavior of the function b, which blows up as t equals to 0. Okay, so we want to try and prove global existence of near Maxwellian solutions and convergence to equilibrium, which is predicted by this H theorem, which I read you in the previous talk. And so the first thing you do is you linearize, and so you take capital F and you write it as mu plus the square root of mu lowercase f, and then the global Maxwellian equilibrium is mu of v is equal to 2 pi to the minus 3 over 2 e to the minus b squared over 2. So we've set the, we've normalized all the constants, which is not a restriction, it just makes your life simpler. And now we derive an equation for this perturbation lowercase f, and the perturbation evolves according to the equation dtf plus v dot grad xf plus L of f is equal to gamma of f, where L and gamma are the linearized collision operators. Gamma is the nonlinear part of the linearized collision operator, and L is the linear part. So I won't go through how you get those, but the idea is that you plug in capital F in this form, and mu plus the square root of mu lowercase f, and you expand, and you end up that gamma is equal to mu to the minus a half q of the square root of mu f, comma square root of mu g, and then L can be expressed in terms of gamma. And we assume that the solution lowercase f to this perturbed equation satisfies the conservation laws in this sense. So we assume the integral over t3 of dx, the integral over r3 of dv of 1 v and v squared square root of mu f is equal to 0. That just says that capital F has the same conservation laws as mu. So we have, if you expand this out, we assume that this part is 0, and that means that your initial solution to the Boltzmann equation has the same conservation laws as the Maxwellian that you're perturbing around, which guarantees that the convergence has to be to this Maxwellian mu. Okay, and in this context, Boltzmann's H theorem says that capital F converges to mu as t goes to infinity, or lowercase f converges to 0. And this is what we want to study. Okay, so we introduce this weighted Sobolev space ns gamma, and we've already seen this. So we write f squared ns gamma is equal to f L2 gamma plus 2s, where L2 gamma plus 2s is defined down here. The gamma plus 2s just defines the power on the weight that you're looking at. And you have this same fractional semi-norm from the previous talk. And we have this Sobolev space, ns gamma. It's a non-isotropic, fractionally diffusive Sobolev space. It's precisely defined. And the thing to point out is that this quadratic difference, v squared minus v prime squared, is absolutely essential. It's not a lower order term. It induces changes in the power of the weight structure that you have in this norm as directions change. Okay, so in this paper with that I wrote with Clement Mouhot in 2007, we conjectured that something like this would happen, but we didn't really know exactly what was going to happen. But now we know, so that's pretty cool. And okay, so in the next slide after this, I'm going to state a main theorem. But in order to do that, in order to state things in a meaningful way, I have to walk you through a technical slide defining complicated Sobolev spaces. So we define a weight function W of v to be the bracket v thing if gamma plus 2s is bigger than 0, where gamma and s are these parameters from the collision operator, and we define it to be v to the minus gamma minus 2s if gamma plus 2s is negative. Notice that both of these things go to infinity as v becomes large, but this scaling is just sort of useful for stating the problem. And now we define, so after that, defining that weight, we define a high order spatial velocity derivative partial alpha beta, where alpha and beta are multi-indices, and the alpha multi-indices denote the spatial derivatives, and the beta multi-indices denote the velocity derivatives. And so then we define the Sobolev space HKL, which is in the torus cross R3 for L and K positive. K obviously has to be an integer because it denotes the order of differentiation, but L can be just any real number. Then the norm, the HKL norm of H squared is just the sum over all multi-indices alpha and beta less than or equal to K of derivatives partial alpha partial beta of H in the standard L2 norm, and then you weight these things by L minus beta. So the more derivatives you have, the fewer weights you have. So there's a couple of them. And then you define a weighted non-isotropic derivative space NS gamma L. You have to be careful about how you define this, so I'll just write it down for you by taking L2 gamma plus 2s of H and adding a WL in there, and then taking the same non-isotropic derivative space, but then you just throw a W2L in there as well. And now you have to define a high order non-isotropic weighted derivative space that I'm calling NS gamma LK. And so now this has L weights and K derivatives, so you sum over multi-indices alpha and beta less than or equal to K, and you throw in all the derivatives alpha and beta into your NS gamma norm, and then you include the indexing of the beta derivatives in the order of the weight.
So here you get space, right?
Yes.
So all the way periodic.
So yes, so the theorem that I'm going to discuss is all the way periodic in space. But we can also do the whole space case, and I'm going to talk about going for the purposes of existence, going from the decay. So I'm going to talk about decay tomorrow in the whole space.
Oh, so the same decay
we have optimal decay rates in the whole space, but they're not the same as the decay rates on the torus.
Right.
The decay in the whole space.
Not exponential.
It's not, you can't, it's hopeless to think of getting exponential decay in the whole space, unless you have some sort of a confining potential or something like that. But, yes. Okay, so the L2 norms denote, in the velocity variables are just denoted by L2, and now we have this theorem that I'll read to you. So this is joined with Phil Glassman, and we fix the number of derivatives k to be bigger than 4, and we fix any weight L bigger than 0, and we choose an initial condition F0 to be in this HKL space that I defined on the previous slide, and we assume that the initial condition satisfies the conservation laws that we talked about previously. Then there exists a number eta such that if F0 HKL and the HKL norm is smaller than eta, then we can prove that there's a unique global classical solution to the Boltzmann equation, which satisfies f of txv is in L infinity, and HKL intersect L2 and NS gamma LK in all variables. So in the time from 0 to infinity, space in the torus, and velocity in R3. And when gamma plus 2s is positive, for a fixed lambda, we have exponential decay. So the HKL norm of f decays exponentially fast to equilibrium. So as time goes to infinity up to constants, this f of HKL is bounded by f0 of HKL times e to the minus lambda t. So exponential convergence to equilibrium. And then when gamma plus 2s is negative for any m, so for any real number m, if f0 of hkl plus m is sufficiently small, then the hkl norm of f decays polynomially fast to equilibrium of order m. And there's, so this is rapid polynomial decay. So for any order m, you have very, very fast polynomial decay, but you have to make additional assumptions on the control of the initial data. And I'm not going to claim that the assumptions that we're making on the initial data are optimal, but I am going to claim that if you don't make additional assumptions on the initial data, in the case gamma plus 2s is negative, then you can have very, very slow decay. There are examples by Carlin and Zhu, in the spatially homogeneous case, finding very, very slow decay rates for self-potential Boltzmann equations even without angular cutoff. And there are examples for model problems which show that you can have very, very slow decay. So I'm saying that you can probably also get exponential decay of the form, so something like, tried to prove this, but we proved this in the cutoff case, and I believe that if you put some kind of an exponential velocity weight on the initial data, then you can get exponential decay to the order p. But so this is stronger assumptions on the initial data. This is weaker assumptions on the initial data, and it's really, really hard in this business to prove lower bounds. So it's hard to say that what you're doing is optimal, but this is pretty fast, and this is pretty fast convergence, so we're sort of happy with that. Okay, so so this exponential decay, you just think that's optimal because it's exponential, and this is rapid polynomial decay, so it can be very, very fast, and so that's we're happy with that too. And so you can also prove positivity. So if you're positive initially, then you're positive for all time. This is sort of a standard argument, so you don't have to work that hard. Okay. Yes.
Condition on upper bound or half case or whole bound or slope case gamma plus 2s. Whatever it can be larger or it can be small.
So what's your
Gamma
question?
plus 2s.
Yes.
Can be small or small. No bound.
Okay, so we are using the conditions gamma is bigger than -3 and s is between 0 and 1. Now you can do any gamma bigger than -3 and any s between 0 and 1. So there's no other additional conditions on gamma and s. You can do any gamma bigger than -n in n dimensions and any s between 0 and 1. You don't need to make any further, we don't need to make any further assumptions on gamma and s. So you can do all of them.
Even gamma plus 2s can less than -3.
No, s is positive.
Oh.
So gamma plus 2s is never less than -2. So we can do all of those cases. Whatever you want. But when gamma plus 2s is positive, the situation is better than when gamma plus 2s is negative. Okay, so I want to state for you another theorem. And this is also interesting, I think, because it's a low regularity theorem. So here, the theme is that we only need two derivatives. So if k is bigger than or equal to 2, then you can choose f0 in L2 or f3 intersect hk of t3, so you only need derivatives in the x variables. And then you suppose all the same stuff, and you suppose gamma plus 2 is positive. Then you have, under the same assumptions, you have global existence, and you have exponential decay to equilibrium, and you can still prove positivity. And this is interesting to me because this is the lowest regularity assumptions that I've ever seen being used to prove global existence for the Boltzmann equation. And so you only need two weak derivatives. So if you really think about it, if you're only using two weak derivatives, then the solution isn't really smooth enough to be a classical solution, and you have to think of the solution being defined in the weak sense, but still you have enough control over the solution so that you can say that it makes sense in all of these spaces, and you can still prove everything you want, and you can still prove uniqueness. Okay, so a thing to point out is that these solutions gain S non-isotropic derivatives in both theorems. Should be pointed out that people have proven the smoothing effects for these solutions, although we weren't really interested in that. But you can, under additional regularity and integrability assumptions, you can prove the C-infinity smoothing effects. You cannot prove it for two derivatives, but you can prove it for, say, bigger than 5 derivatives in all variables. And we have exponential decay here if gamma is negative. So if gamma is bigger than 2s and less than 0, then gamma plus 2s is positive. And in that case, you have exponential decay. And the thing to be pointed out is that due to counterexamples by Carlin and Zhu, this is probably false without cutoff. So you have a faster decay with this angular singularity than you would if you didn't have it. And the last thing to point out is that this sort of low regularity existence result holds more generally if gamma plus 2s is bigger than minus n over 2 in n dimensions. So, and this includes sort of all physically meaningful interactions coming from an inverse power law potential, although it doesn't cover all of those cases, which may be interesting from a mathematical point of view. Okay, so those are our theorems. So there's not that much known about the Boltzmann equation without angular cutoff. I should say the first thing I want to say is that this very nice CPAN result from 2002 of Alexander and Villani showing the global existence of de Pernet-Leon's renormalized weak solutions with defect measure. Now I'm writing, since everyone always asks me what that means, I'm writing down the exact notion of the solution. So you take a renormalization beta of f is equal to something like f over 1 plus f, and then you apply that to the equation, and then you have this equation should be satisfied in the weak sense. And so these solutions satisfy the mass conservation but not energy conservation. The next thing is this very smart team of guys, Alexander Morimoto, Yukai, Yu, and Yang, have proven related, similar results to what we did. Very nice results, but very different methods. So they have this norm, which is defined in terms of the Boltzmann collision operator, in terms of the collision kernel B, without this sharp geometric diffusive information, but still a very, very nice result. Very clever. So they're okay. So that's it. So the next thing I want to talk about is this resolution of a conjecture that I made with Clément Moureau in this JMPA paper. So the linearized collision operator L is a non-negative, and it has a null space, and this null space is given by this the span of the square root of mu, v1 square root of mu, v2, v3 square root of mu, times v squared square root of mu. And so then you can expand the any function in terms of its projection into this null space. But notice that this null space is 5-dimensional in velocity, and it's infinite dimensional in t and x. And so you define p to be the orthogonal projection into this null space, and then you get this collection of functions. And now L of g is equal to 0 if and only if g is equal to the projection of g, if and only if g lives in this null space. And so what we can prove, again with Phil Gressman, is that the L2 inner product of L of g and g is controlled sharply above and below with constructive constants by I minus pg in this ns gamma space. So the ns gamma space contains the sharp information about the way the linearized collision operator L behaves in L2. And we have constructive constants. So this, in everything we're doing, all these constants are constructive, and they can be tracked if you wanted to do so, although we don't. We make no effort to try and do that, because it would be quite a tedious exercise. And then, okay, so this shows that a spectral gap for this operator L exists if and only if gamma plus 2s is bigger than 0. And that was the thing that we conjectured, is that the operator L has a spectral gap if the parameters gamma and s satisfy gamma plus 2s bigger than 0. It does not have a spectral gap if gamma plus 2s is negative, and that's the reason why you get this sub-exponential decay for the case when there isn't a spectral gap. Okay. Next thing I want to talk about are entropy production estimates, because these are important too. So you could think of the Boltzmann entropy function on the ddt of integral of f log f is equal to the integral over x of d of f, and d of f is this non-negative entropy production functional, which can be expressed as you see here in this funky way. So it's just the integral dv of q of f log of f. And you have this really nice breakthrough coercive estimate of Alexander David Villani and Wenberg, which shows that d of f is coercively controlled by a constant which depends upon r times the square root of f in hs dot with over a ball radius r. So this is a local estimate minus lower order term. And this estimate can be proved under general conditions that I won't mention too carefully. So now we can prove a new entropy production estimate, which is sharp, which is in terms of this same semi-norm that we use for the equation. So d of f is greater than or equal to the integral dv, the integral dv prime of dv, v prime less than or equal to 1, and then you have this bracket v to the gamma plus 2s plus 1, and then you have the square root of f prime minus the square root of f squared divided by dv v prime to the 3 plus 2s. So this estimate is an improvement, and this is remarkably the same semi-norm as in the linearized context, which shows that this space is really controls the nonlinear behavior of the collision operator, and this is a stronger global anisotropic semi-norm than in the previous estimate from the previous slide, because you're integrating over the whole space, you're not restricting to a ball, and you're getting this global anisotropic fractional diffusive behavior, which seems to be an essential component of the Boltzmann collision operator. And the derivative estimate holds under general local conditions. F is in L log L intersect L1. Okay, And I should also point out that a couple other teams of guys, these guys Chen and He and the EMUXY team have proven global entropy reproduction estimates, but if I'm not mistaken, they proved them in terms of isotropic spaces, which is the sharp lower bound for this space. So this space is stronger, and it's because it's non-isotropic, and it has this D metric, which we've talked about. Okay, so that's that. So now I want to explain to you how we a few elements of how we prove this theorem, and I'm going to start with a toy model, which is the one-dimensional heat equation, and suppose that, because it is really illustrative, suppose u is a periodic solution to the heat equation, dtu is equal to the second derivative in space of u, and then you can multiply both sides of the heat equation by u and integrate with respect to x, and you get the following, and then you can pull the time derivative out, and you get the time derivative of the integral of u squared, and you can integrate by parts on the x derivatives, and you get the partial derivative of x squared. This works because you have periodic boundary conditions, and so the boundary conditions disappear. And so from here we see that square integral solutions of the heat equation have norms which decrease in time, and we can even add nonlinear terms to this equation as long as they can be shown to be small relative to the square of the integral of du. And now you have norms which decrease in time, and that's sort of like the magic thing that you look for, some sort of monotonic norm, so that you can say that you have good bounds on your solution. Okay, so let's do a slightly more complicated toy model. So we consider the heat equation plus C of u, where C is some positive number. And this time, if you multiply by u and integrate by parts, you get the time derivative of the square norm of u is equal to negative of the integral of the square of the derivative of u minus c u squared. And the sign of the right-hand side is ambiguous because you have a minus and then you have another minus, and you have this derivative and that derivative. But you can split u into u0 plus v, where v is a function that has mean 0. And so you can always split u as a function that only depends upon time, and a function which has mean 0 just by subtracting off the mean. And now, since this equation is linear, there's no interaction between u0 and v, and we obtain that d squared u0 minus c u0 is one equation which you can solve. And then the equation that you get for v is d dt v squared minus the integral of v of x squared plus c of v squared. And then the magic thing that happens here is that you can use the Poincare inequality, or in one dimensions this is called Werdinger's inequality, to see that what you actually have is this quantity up here is less than or equal to the negative of the gradient of v squared times this constant. And if c is less than 4 pi squared, then you have a norm which decreases in time, and you have nice monotonic norms, and you're happy. This is, in some sense, the easiest example I could come up with of what we're trying to do. Although what we're actually trying to do gets significantly more cumbersome than this. Okay, so the first thing to point out is that our proof is built on previous works by myself and my thesis advisor and Yang Guo for the Landau equation. So Yang Guo has this series of papers where he does macroscopic space-time estimates and a nonlinear energy method. And then in this paper that I wrote with him, we prove asymptotic convergence rates for soft potential Boltzmann equations with cutoff. And but this machinery that we're trying to employ breaks down at the following stage. So you need to find a Hilbert space X such that the nonlinear term is bounded above as follows. The L2 inner product of the nonlinear term for functions g, h, and f is bounded by g and L2, h and x, f and x plus lower order terms, and L of ff is bounded below by f and x squared minus lower order terms. And you need these lower order terms in order to understand in order to get away from the null space. And because of the intricate connections between L and F, L and gamma, excuse me, if such a Hilbert space exists, then it's sort of essentially unique. And the question is, how do you find this Hilbert space? And I guess the answer is I already showed you what it was. It's n as gamma. So the first thing that we had to figure out was what is n as gamma. And so you really, really need this crazy space n as gamma. It's sharp, and it's essential to use. And now, so by analogy with the heat equation, the general idea is you have this equation dTF plus B dot xF plus L of F is equal to gamma FF, and we define a high order norm that I call G, and it's equal to f of hk squared plus the integral from 0 to t of f of n as gamma squared, and you throw in some spatial derivatives for good measure. And then if you multiply this equation up here by f, and you integrate over space and velocities, so you integrate over t3 cos r3, then you obtain the inequality right here. Where you obtain the inequality here. You have the time derivative of f in L2 squared plus the inner product of L of ff in L2 is equal to f inner product with gamma of ff with the L2 inner product. And that's just because the spatial term disappears when you integrate. Okay, so the key steps to prove nonlinear stability are to prove that G is, in some sense, controlled by the initial data. So if you can show that the G norm of the solution is bounded above by constants, and which don't depend on the initial data times the norm of the initial data, then you're in good shape and you're happy. And then you expect that you can prove nonlinear stability. So things that we want to prove are a coercive estimate. So we want to prove that L of F is bounded above by f n as gamma squared. And this is false as an operator inequality. It's only true for solutions to the equation, amazingly, because of this null space. And you also want to prove a nonlinear estimate. So you want to prove that f gamma of ff in L2 is bounded above by f L2 squared plus f squared n is gamma. And if you can prove these two inequalities, and if f is sufficiently small, then you can prove this blue inequality up here. And so this is the highest level strategy of what we're trying to do. Okay, so what I want to talk about for the rest of my time is how we prove this. And so we want to prove a collection of estimates. So we simplify the linearized collision operator by writing L is equal to n plus k, where n is essentially the norm and k is a compact perturbation of the norm. And then we want to prove a norm estimate, ngg in L2 is basically the same as g in n as gamma squared. And so these two are equivalent. Then we want to prove a compact estimate. So we call k compact, meaning in the sense that this estimate is true. So k, g, g in L2 is bounded above by eta times g in L2 gamma plus 2s, where eta is any arbitrarily small number plus a large constant c of eta times g in L2 in a ball of center 0 and radius c of eta. So eta can be arbitrarily small, but as eta goes to 0, c of eta goes to infinity. But c of eta is finite for any small finite eta. You want to prove an estimate like this, and then you want to prove a nonlinear estimate like gamma of g, h, and f in L2 is bounded above by GL2 H NS gamma F NS gamma. And if you can prove all three of these estimates, you'd be very happy and you'd be well on your way to proving the main theorem. Okay, so to simplify our presentation, we explain our estimates without velocity derivatives. And so I just want to say that things are actually more complicated than this, but this is complicated enough to get the main ideas. For the very, very soft potentials, when gamma plus 2s is less than minus n over 2, in n dimensions, velocity derivatives are important, but for our purposes, we're not going to explain that part. Okay. So the first thing I want to explain to you is something that we call the main coercive inequality. So this operator n, which I haven't explained, can be written as and n is the norm part of the linearized operator, so it has a complicated expression, but it turns out that after doing something called a Carleman change of variables, you can write it essentially as the integral R3 dv, integral R3 dv prime, times k of vv prime g prime minus g squared, plus the integral of dv of bracket v of gamma plus 2s times g squared. So you can do something that's sort of like what's usually called a Carleman change of variables and get this exact expression, except for what you don't have is v to the gamma plus 2s. You have an operator which behaves like that. Whatever. Okay. So a pointwise estimate of this function k shows the following. So what we want to prove is that mgg has a lower bound in terms of this ns gamma space. And so to prove that, the natural thing to do is to estimate k from below pointwise. And what you get is that k is bounded from below pointwise by this parabolic distance d of vv prime to the minus 3 minus 2s. That's good. And then you get bracket v of the gamma plus 2s plus 1. That's good. And then you get the indicator function of dvv prime less than or equal to 1. That's good. And if you could prove all of that, then you'd be done. But unfortunately, you can't prove all that. You have to include this extra indicator function of the region where v squared minus v prime squared in absolute value is less than or equal to v minus v prime. And this seems to be pretty close to the best you can do in terms of pointwise lower bound. So this pointwise lower bound is false without this additional condition. You would have to include an exponentially decaying factor without this additional condition, and that's an indication of the fact that you have non-Euclidean geometry, the fact that you're sitting on this paraboloid in some sense, and you have this parabolic geometry going on. Okay, so if you can't prove this for pointwise lower bound, what do you do? So it turns out that even though the pointwise inequality is false, you can actually prove an integral inequality. So if you plug this pointwise inequality into this integral, then you get a pointwise expression which seems to be smaller than this one. But nonetheless, since you're integrating, you can connect all the pieces together and actually get the lower bound over the full region without this extra space. And the idea is that you can resort to the Fourier Transform, and you can show that if two kernels compare with each other on the Fourier Transform side of things, then the integrals are comparable. And so what we do is we partition space up into small balls, and we use a partition of unity to do that. And then we take the Fourier Transform of everything. We use Plancherel's identity. And we show that each of the pieces with this extra restriction are in fact comparable to the same piece without that restriction on the Fourier side. And then you can go back to the original place. you can go back to the original non-Fourier variables just by using exponential again. Okay, so that, we call that Fourier redistribution. So this is the first step, and this is what we call the main coercive inequality. And the next big step that I want to talk about is the so-called geometric Littlewood-Paley-Stein theory on mass shells. So normally when people do Littlewood-Paley theory, they do isotropic Littlewood-Paley theory. This is a non-isotropic Littlewood-Paley theory. And the advantage of the concrete definition of this space NS gamma is that we can develop a Littlewood-Paley theory on, I like to think of it as Littlewood-Paley theory on the mass shell. So you define Pj and you think of f, and you think of it as a function of 4 variables, v and v squared, and you basically do 4-dimensional Littlewood-Paley theory, and then you restrict down to 3 dimensions on this mass shell, and you renormalize everything. And what you get is integral over R3 dv prime of 2 to the 3j and phi of these the difference between v and v prime, and then the difference between v squared and v prime squared. And then you have to renormalize everything so that it's true 3-dimensional Littlewood-Paley theory. And then you define a qj to be the difference between pj and pj minus 1f. So this is a renormalized 4-dimensional Littlewood-Paley theory decomposition of the measure on the paraboloid in R4. And we can phrase our estimates in terms of pj and qj and Euclidean derivatives of these functions on R4 instead of R3. So we can obtain sharp characterizations of the space N gamma, NS gamma in terms of the Littlewood-Paley square function of qj. So for any multi-index alpha of Euclidean 4-dimensional derivatives where nabla tilde is the 4-dimensional gradient, then you obtain the sum from j equals 0 to infinity of 2 to the 2s minus alpha j of the integral of R3 of this nabla alpha of qj of f squared times v bracket to the gamma plus 2s is controlled by the NS gamma. And so the point is going to be that we're going to expand all our functions in terms of these Littlewood-Paley projections, and then we're going to prove estimates for each of these pieces, and we're going to understand the power of the non-isotropic derivative in terms of a bunch of 2's to certain powers, 2 to the sj and things like that. And then we're going to sum everything and use Cauchy-Schwarz for summations a lot and compare everything back to NS gamma. Okay, so since that slide was a little bit dense, I thought I would show you a picture to illustrate what's going on here. So if you would have decomposed things in terms of R3, what you would have gotten is that the derivatives, when they're thought of as waves, look, this is a cartoon, but they look sort of like this. And the point here is that the wavelength changes. So the wavelength here is different from the wavelength here. It's not uniform, and there's a big problem. But then if you sort of stretch things out, if you sort of pull the wave into this paraboloid, then you get a uniform wavelength everywhere. So the wavelength along the paraboloid is uniform. It's the same. And if you look at things on the paraboloid, and that's why, and this is the way the Boltzmann equation looks at things, and this is the way isotropic people look at things. And the problem to sort of understanding that enabled us to do our analysis was that we could sort of figure out that the right thing to do is to stretch things out onto this paraboloid. Okay, so that's the picture. Let me skip this slide. Okay, so the next thing I want to do is a non-isotropic, what I call a non-isotropic dyadic decomposition of the singularity. So let chi k be a partition of unity on 0 infinity, such that chi k is bounded, and each chi k is supported on 2 to the minus k minus 1 to 2 to the minus k. So you have these collection of functions which partition unity and which are supported on dyadic intervals. And then you define the kernel bk to be the kernel b times this chi k function, where chi k is a function of the modulus of v minus v star, and we call this a non-isotropic decomposition because it enforces that the angle between v minus v star and sigma is proportional to 2 to the minus k times v minus v star to the minus 1. And now you define decomposed gain and loss operators by tk plus and tk minus is equal to the integral over all the variables times bk times g star h m prime star and f prime, where m is the square root of mu. And now you can expand. So the thing to point out here is that even though b, the integral over sigma of b is infinite, we have chopped up the singularity so that each of these terms is finite. And now you can take the L2 inner product of gamma g, h, and f, and you can expand it as a sum from k equal minus infinity plus infinity of tk plus minus tk minus. Now you can estimate each of these terms individually. And so the point here is that our decomposition of the collision kernel B allows us to say that the integral over S2 of B is bounded above by 2 to the sk v minus v star to the gamma plus 2s, just by standard, by using the formula for B and by integrating. And then you get these so-called gain-loss estimates for these pieces. So you have tk plus and tk minus are bounded above by 2 to the sk gl2 hl2 gamma plus 2s and fl2 gamma plus 2s, where these are these weighted spaces. Okay, and now, so these are good estimates when you're far from the singularity. Because so for example, when k is negative, then this gives you a negative power of 2, and that's good because it has a decaying factor. But when k is positive, this gives you an increasingly growing factor of 2, and that's bad because it goes to infinity. So when k is positive, you have to do something else, and so we have to measure differences using the path traced by the parabola. So we define gamma bar of theta to be theta v prime plus 1 minus theta v prime, and then the same thing in the parabolic distance. And then you can take two functions which are thought of as being on this parabola, one at v prime and one at v prime star, and you can write them as the derivative of an integral of the function along this path. And then you can take this derivative and you get the integral from 0 to 1 d theta of d gamma over d theta dotted with the four-dimensional gradient of f, where this is the Euclidean dot product in our form. That's what you get. And then we define the absolute value to the k of f to be the maximum of all of these derivatives in whatever direction you want. And so this is just the maximum of the derivatives for k equals 0, 1, or 2, say. And so now we need to, so with this, we can prove better estimates when k is positive. So we suppose that f is some Schwartz function, which is given by the restriction of a four-dimensional Schwartz function to the paraboloid, and we let f squared be the restriction of the same function to the paraboloid. Then you can prove point-wise estimates, tk plus minus tk minus, so that when you take these cancellations into account, you can prove that you get a better power of 2 here. So you get 2 to the 2s minus 2 to the power of k. And now when k is positive, this is negative because s is between 0 and 1, so you have a decreasing power of 2. So again, that's your friend. And then you have g L2, h L2 gamma plus 2s. We have to pay for this extra power of 2 by putting derivatives, 2 of these non-isotropic 4-dimensional derivatives on f. And you can do a similar thing for h. So you can prove a similar estimate instead of putting derivatives on h, instead of putting derivatives on f, and you gain some power of 2. Okay, so now what do you do? The idea is that we want to prove estimates for the L2 inner product of gamma, g, h, and f. And so what we do is we do triple sums. So we expand everything in terms of all the machinery that have been developing. So we sum over the singularity. So gamma k is gamma with the kernel bk. We sum from k equals minus infinity to infinity. And then we sum over, we expand f and h in terms of these non-isotropic little Paley projections. And we sum over j going from 0 to infinity and L going from 0 to infinity, and you get 2 terms depending upon which side of the diagonal you're on. And so you get these 2 triple sums that you need to estimate. And for this second triple sum, you use the cancellation estimates on f, and for the first triple sum, you use the cancellation estimates on h. And so we think about this heuristically as 2 terms. So we sum, this big sum is equal to the red sum, where the key point about the red sum is that you sum from k equal minus infinity to j, and for the blue sum, you sum from k equal j to infinity. So the red sum is far away from the singularity, and the blue sum is near the singularity. And you can control these sums by collecting all the previous pieces. And you notice that when 2 to the minus k is large relative to 2 to the minus j, we are far from the singularity. And we use the size and support estimates. We use the first estimates that I wrote down. And then when 2 to the minus j is large relative to 2 to the minus k, we are near the singularity. And in that case, we use the cancellation estimates, and we just sort of collect all the machinery that we've used in the previous slides, and we sum, and we use a lot of Cauchy-Schwarz, and we use the square function estimates and the cancellation estimates and the size and support estimates, and we put them all together, and we use it. Then we notice that this square function is comparable to the NS gamma norm, and we get our desired estimate for gamma from collecting all this stuff. Okay, so I think I'm out of time. So thank you. If you want to read about it, that's great. So on tomorrow morning, I'm going to be talking about something completely different, so you won't need to have remembered any of this stuff at all. I'm going to be talking about optimal time decay rates for kinetic equations, and it studies the same equation, but it uses a completely different set of tools. So thank you.